Okay, welcome back. This is Mr. Hassan's Maths channel. I'm now answering question number 6 from the May-June 2022 Cambridge 9709 syllabus. This is the A-level syllabus. This is paper 1, variant 1 from the pure maths. And this question here is about functions. It says the function f is defined as follows. F of x equals x squared minus 4 over x squared plus 4 for x is greater than 2. Find an expression for the inverse of f of x. So in this case here, when we want to find the inverse of a function, okay, and we just want to find the expression, so therefore we don't have to find the domain of the inverse, just the expression for the inverse, then what we're going to do first is, first step, we'll say let y equals f of x. So we're going to rename f of x as y. So have y equals x squared minus 4 over x squared plus 4. Now what I like to do is I like to replace the x and y at this stage so I don't forget at the end. So I'm going to swap the x's and the y. So wherever I see x, I'm going to call it y. Wherever I see x, I'm going to call it, wherever I see y, I'm going to call it x. So y becomes x squared becomes y squared, and this x squared also becomes y squared. So you end up with x equals y squared minus 4 over y squared plus 4. Now when I take this and I make y the subject of this, then I will have the form of the inverse. So the first step is to get rid of the fraction. So I'm going to multiply both sides by y squared plus 4. So that will give you something like this. Now we want to make y the subject. So I have to kind of release this y squared from this bracket by expanding this bracket. So x times y squared is xy squared. X times 4 is 4x. And that's equal to y squared minus 4. Now I want to bring the y's together. All right. Now, what I could do is I could say x squared, xy squared minus y squared equals, and I have minus x minus 4x, which would be fine, but it looks a bit, doesn't look very nice to have minus and a minus like that together. So what I'm going to do is I'm going to do something to make it look a bit better. I'll say I'll keep the y squareds on this side. So this is going to be y squared, take away xy squareds from that side. And this side has 4x and add 4 to both sides. It looks a bit neater that way. And I want to make y squared the subject, so I'm going to take y squared as a common factor of these two terms. So y squared times 1 is y squared, and y squared times minus x is xy squared. So that's factorized. This stays as it is for now. We don't have to factorize it. But what we can do now is we can divide both sides by 1 minus x. So we have 4x plus 4 divided by 1 minus x equals y squared. So therefore we can say y equals the positive or negative square root of 4x plus 4 over 1 minus x. Now, when we write the inverse function, we can't write both positive and negative square roots, because what will happen is it won't be a function then, okay? Because it's gonna, one second, sorry, it's going to be a one-to-many. It won't be a function. All right, so we have to choose, when we write our inverse function now, we have to make a choice. Are we going to write the positive or the negative square root of this? Now, the general rule is if the domain has been restricted such that it is to the right of a particular value, you could say to the right of the vertex, we could say, okay, then we're going to have something which is, we will take the positive square root. If it's been restricted to the left of the vertex of the, function, then it's going to have a negative square root. So in this case, because it's to the right, we'll just assume it's to the right of the vertex. We don't actually know where the vertex. This is not a very easy function for us to picture, okay? Although it is possible for you to try and figure out how it looks. Okay, there are ways to do it, but generally, if it says greater than, then you'll take the positive square root. If it says less than, and normally you'll take the negative square root. I don't think they're going to give you anything too complicated here. So I'm going to leave this as positive, the square root of 4x plus 4 over 1 minus x. Don't write plus or minus here. Okay, so there's the answer for part A. Now for part B. Show that 1 minus 8 over x squared plus 4 can be expressed as x squared minus 4 over x squared plus 4, and hence state the range of f. So we want to find the range of this function, okay? And they're helping us in a way by making us express it, showing us that this and this are the same thing. So first we have to actually show how this becomes the same as what we have. So basically what we can see, we have two terms. This is one term. Let's add these two terms together. So it's like algebraic fractions. Let's make the denominator the same. This is like 1 over 1. If you make the denominator the same, this becomes x squared plus 4 as the denominator. And the top is also x squared plus 4. And this already has that denominator. So we can now simply, write it as one denominator, x squared plus 4. And we have x squared plus 4 minus 8. And that gives you x squared minus 4 over x squared plus 4. You need to show the steps clearly because you were told, show that this can be expressed like that. So, you have to show the steps very clearly. You can't just write that equals that. You have to show how we got there in like proper steps. Now, and hence state the range of f. So now what we can say is the function f of x can be written as 1 minus 8 over x squared plus 4. Now, writing in this form will help us to work out the inverse function. Sorry, the range of the function, not the inverse function, the range of the function. Now, there are a number of ways we can actually try to work out what the range of this function is. Remember, this function is defined for x values which are greater than 2. Okay, so we want to find the range of the function. We want to find what are the possible outputs, what are the possible y values that this can take if we know that x is greater than 2. All right, now, first of all, we have, this looks like a reciprocal type of function. Now, reciprocal functions normally have an asymptote. Okay, now there's no asymptote on the x-axis because the denominator can never be 0. X squared plus 4, it can never become 0. So there's no problem, there's no value for x for which this is undefined. So it will be, the domain will be, x is greater than 2, and even if it wasn't restricted, there would be no restriction for it at all. It's restricted because that's how this function has been given to us. But for the y, it seems like there's an asymptote y equals 1. Normally when you have this type of graph, okay, where you have a reciprocal type of equation, where you have x in one of the denominators, if you have something added to it, that number is normally the asymptote, the horizontal asymptote. It's normally y equals that number. And let's confirm that. Like if I was to take y equals 1 minus 8 over x squared minus 4, and I was to make y equals 1, then you'd have something like this. If you try to solve this, you'll have 0 equals minus 8 over x squared minus 4. And when you try to solve it now, you multiply both sides by x squared minus 4, you get what's called a contradiction. That doesn't make sense. All right, so there's no solution. So when y equals 1, it's undefined. Okay, even if you took this, x squared minus 4 over x squared plus 4, and you make it equal to 1, if you try to solve it in this form, you'll have x squared minus 4 equals x squared plus 4. You multiply both sides by x squared plus 4, you get something like this. When you try to solve it, bring the x squares together, they'll cancel out. You'll have minus 4 equals 4, which again is a contradiction. Doesn't make sense. Okay, so whichever form you try to solve it, y equals 1 causes a contradiction. So we can say y equals 1 is an asymptote. Okay, all right, so that's one thing. So I'm going to draw a little sketch because sketching always helps us to answer such questions. So I've got my y-axis. I know that there's an asymptote at y equals 1 for sure. Just determine that. Okay, so there's an asymptote at y equals 1. Say that is y equals 1. Okay, so y equals 1 is an asymptote. Now, next, what else do I know? We know that the function starts from 2. Not including 2, just x is greater than 2. All right, so it starts from there. So let's see what happens as, for example, x is close to 2. So let's see when x equals 2, you're going to have f2 equals 1 minus 8 over 2 squared plus 4, which is 8, which is going to be 0. So 1 minus 0, which is going to be, 1 minus 1. 8 over 8 is 0, is 8 over 8 is 1, which gives you 0. 1 minus 1, which is 0. So it's going to start off from here. Okay, and we can see that it's going to get closer to 1. All right, because that's the asymptote. And we can confirm that. We can say as x approaches positive infinity, then y will approach 1 minus 8 over positive infinity, because Infinity squared plus 4 is going to be a really huge number, which means that's 1 minus and something divided by infinity. If I did 8 divided by something really big, it's going to give me a small number. It's going to approach 0. So it's 1 minus 0, which is 1. As we determined, y equals 1 is the asymptote. So this function is going to only be ranging between these two values, between 0 and 1. Okay, so this will be the range of this function, the output, the y values it can take. Okay, it's going to be between 0 and 1. Okay, between 0 and 1. Come on, move. Okay, so this is 1 here. Okay, so it's going to be greater than 0 because it doesn't include 2. It's greater than 2. And it doesn't include 1 because it's asymptote. So we can say that the range of f of x, its range is between 0 and 1. Okay, and we can see that algebraically that's also true as well, because we know that x is greater than 2. So the lowest x can get is just above 2, which is just above 0. 1 minus the output when you put x equals 2, as we saw, was going to be 0. That's going to be 4 plus 4, which is 8. 8 over 8 is 1. 1 minus 1 is 0. So it's going to be, if x is greater than 2, it's going to be something just above 0 first. And you can see that, as x gets bigger and bigger and bigger, this value gets really big. So the lowest that this value can be with this condition is going to be 8, just above 8. So this will always be a fraction less than 1. So you're always going to have 1 minus something. And as x gets bigger, the value of this fraction gets smaller and smaller and smaller. And the value of the whole thing gets closer to 1. So you can see that almost algebraically as well. And you can see that using a little sketch here. Now the sketch wasn't made because I know how this graph looks, but I knew there's an asymptote at 1. And I knew that when x is equal to 2, we're at 0. And I know that as x gets larger and larger and larger, this thing gets, as we can see from here, from this, gets closer to 1. All right, so that's how we know the range of this function. I hope that's clear. All right, it's a very important points here. They're not really worth that many marks, to be honest. I think most of it would be by showing this. Maybe you might get 2 marks for that if we look at the mark scheme. But it's important that we understand how to do it. They won't really expect you to show any explanation for this. You can just write the answer down. It says, and hence state the range of f. So if you just did that and you just thought about it in your head and you wrote the answer down, that would get you the full marks. You don't have to show any reasoning for it. It's just state the range of f. Okay, but it's good to understand why. So that's part B. Now for part C, explain why the composite function ff cannot be formed. Now, a composite function can only exist if the input or if the output or the range of the inner function, okay, is something that can go into the outer function. So when you have a composite function, in this case, they've asked us f of x. So we got to take the function f and put it inside the function f. Now, what can come out of here, what comes out of here must be able to go into this function. Okay, so we know that for f of x, we know that the range, as we just saw, is between 0 and 1. And we know for f of x, the domain, as we've been given, is x is greater than 2. All right, so this function has to go inside that function. Okay, does this domain, so the output of f of x will be a value between 0 and 1. Okay, it will be a value between 0 and 1. Okay, now does that fit into the values which are greater than 2? No. Okay, so what goes into here, must be a value between 0 and must be greater than 2. Okay, f of x must be greater than 2. Okay, all right, it must be for it to go into here. And it's not. F of x is not greater than 2. F of x is between 0 and 1. F of x is between 0 and 1. It's output. Okay, so we can say that the output, the range, or the output, we can say, the output of f of x does not, or isn't included in, is not included in, isn't completely, in fact, it's not complete, it's not at all complete, isn't, it's not at all, within, isn't completely included within the domain, the input of f of x. Okay, because f of x is both the input and the, the inner and the outer function. Okay, therefore, the composite function, composite f of x, cannot be formed, as they stated. Cannot be formed. Okay, so you must mention something like that. Okay, so what comes out of f of x doesn't fit into f of x. Okay, the output of f of x does not go into the domain of f of x, so the function ff cannot be formed. All right, so that's the answer to that part of the question. And that completes this question number 6 from the May-June 2022 paper from Cambridge, Pure Mathematics 1. Other questions from this particular paper will be found in the playlist that will appear in this section over here. Other questions from the topic of functions from Cambridge can be found in the playlist over here. You can subscribe to my channel by clicking on this link, and this video here, which will be linked here, shows you how to use my channel to find what you're looking for. Thank you for watching, and see you soon.